Okay, so here we're ready to start the classic calculus problem about the box. We want to maximize the volume of that box. In this case, we've been given a square base, and so I just briefly want to say that if this base is square, let's call that x, let's call that x, and let's call that y, the volume will be x times y. And when I put it all together, x times y, I will get x squared y. I'm unhappy about there being two variables here. So I'd like to find any other piece of information I could to try and help me with this problem. And I'm noticing right there that it says it's to be made from 48 centimeters squared of material. And so I'm thinking about it, it's like they've got a big piece of cardboard, right? And that the area of that is going to be 48 centimeters squared. And they're trying to fold this, square area into the three-dimensional shape. And the way that they do that is not really my problem, but I will mention that I know that I don't have any more than this 48 centimeters squared of that material. So I'm saying that if I do know the area that I'm working with, I could think about the area of this piece and that piece and the back piece and the other back piece, and I could add all of those up, and I know I shouldn't get um, oh yeah, don't forget to add the bottom one too, that I have those five sides and that those five sides added together, if I take the surface area of each of those pieces and add them together, I should get 48. So I'm going to say then that the surface area that I have that I can work with is the bottom piece, which is x squared, and then four of these side pieces, which has the dimensions of x times y. And now that I know that, I could actually say, go ahead and say, you know what? I know what the surface area is. That surface area is 48. And now I'm thinking I'm going to take this information in green and move it into the volume formula so that I have fewer variables over there. So I don't want to have to deal with so many variables. I'm sure that there's a way for me to simplify this problem, and that's how I'm going to proceed. And so basically what I've done here is step one of the procedure and step two of the procedure. That's where that's where I'm trying to get to. So this is one and this is part of one. And now I'm going to solve for, well, look, I have y only in one place, so why don't I solve for y? So I'm going to say 4xy equals, ready, 48 minus x squared. So I have 48 minus x squared. Okay, and then I'm going to divide by 4x, and I'm going to divide by 4x. And now I can say that y equals 48 minus x squared over 4x. And I'm going to plug that in right here. So I could say that the volume is equal to x squared times y, which is 48 minus x squared over 4x. And I'm thinking to myself about this problem. Hey, I've got an x squared on top. I've got an x on bottom. There's still an x left when I simplify that. And then each piece, is even more simplifiable. I could say that I have 48 over 4 and minus x squared over 4. And I could keep finishing this problem by saying that I have 48 over 4. This is 12x. And right here, this is an x cubed being multiplied technically by a 1/4. Okay? And so that is my new volume formula. Now it says rewrite with only one variable on each side. This may require a secondary equation. I did that. All right. So step 4, find the domain. I want you to know that the domain is coming from this equation because I have these limits, these hard limits of it being a 48 centimeters squared. So if I look at the top of this equation, so I'm doing step 4, finding the domain. If I look at the top of this equation, if I have 48 minus x squared equals 0, then I could find out how to make my, how to find the zeros of this function, or try to find out where I might maximum value that x could possibly be. And so I say that this is 48 equals x squared, and then I'm going to take the square root of both sides, and I'm going to say that the domain is restricted to starting at 0, not exactly equaling 0, because we know that if x was 0, this part would be troublesome. And then here, the square root of 48 is the smallest. Sorry, the largest value that I could possibly get there. Okay, so now I've figured out the domain. I want to take the derivative, and I'm going to say, because that's step number 5 here. Here we are finally on step 5. Take the derivative, find the critical numbers, make a number line, etc. See if we can't determine a maximum for the length of the side of this bottom piece. And once I know what x needs to be, I can determine what y should be as well. So here I'm going to say step 5 is to take the derivative, and I say v prime equals 12x minus 1/4 times 3x squared. And that wasn't too painful. And in fact, I'm going to clean it up just a little bit. 12x minus 3/4 times x squared. And I want to know, hey, how do I get, oops, sorry, that's a 12. My bad. This is a 12. Okay, now I want to know how to set this, how to find the maximums, how to find my critical number. So I set that equal to 0, and I say that I have 3/4 x squared equals 12, and then I'm going to multiply by 4/3 on both sides, and I say that I have x squared is equal to 16, and so x equals, well, technically it's positive and negative 4, but I don't really care about the negative 4 because there's going to be no negative lengths here in this problem. So I'm saying, boom, I think I found my critical number, and I want to do the first derivative test on it to see if I can determine that it is indeed my critical number. And again, I have a domain here from 0 to the square root of 48. And then inside of here is 4. Now some of you might be freaking out a little bit about the square root of 48. Let me assure you that you know stuff about the square root of 48. For example, the square root of 49 is equal to 7. So this is slightly less than 7. Okay, and so since we know that it's some number like 6.9 or 6.8 or whatever, 4 is going to be over here somewhere on the number line. 4 is not going to be over there on the number line. Okay, so now that I've positioned 4 here, I want to go back to my derivative, and I want to say to myself, well, what happens if I plug in a number that's smaller than 4? Like say, for example, I'm going to test a 2. So if I plug in a 2 right here, then I get 4, and then I take 3/4 of it. And I'm just saying that 3/4 of 4 is definitely not going to be as big as 12. So that means this value is positive. Okay, cool. And then let's say I want to pick a number that's bigger than 4, like for example 6, and not 10 here, because I know you guys know that my favorite number to test is 10, but 10 would be over here outside of the domain, so I can't do 10. So I'm going to do 6, and I'm going to plug in a 6 here, and I'm going to say this is 3/4 of 36, which is, again, definitely going to be a value that I can compare to 12, as in it's, let's see, 3/4 of 36 is definitely going to be something that will be bigger than 12. And so if I take it away, I will get a minus sign here. So what I have is a slope that is increasing, and then it is decreasing, which means that I have a local max. And that local max is at x equals 4. Yay. Now I go back to my original equation up here for the surface area, and I'm going to plug that in so I can find out what y is. So I'm going to say I have 4 squared plus 4 times 4 times y, and that equals 48. And this is a pretty easy equation to deal with. So I'm going to finish it up. Minus 16 minus 16. I get 16y equals 48 minus 16 is 32. I'm going to divide by 16 and divide by 16, and I just found out that x equals 4 is one part and y equals 2 is the other, and this should be the maximum box. Now, you're like, well, how do you